Hello everyone. Welcome to the EasyPower Tuesday Refresher Series. My name is Jim Chastain. I'm with the Applications Group here at EasyPower. And the topic today is something that actually comes up more often than you'd expect. Probably easily a third of the EasyPower users are involved somewhat in the utility distribution world, or some have campuses where we have high voltage, high tension wire runs that have medium voltage in their system. And the question is how to handle arc flash greater than 15,000 volts. Well, this situation's been exacerbated by the fact that the recently updated IEEE 1584 standard specifically makes a point of not making a recommendation for voltages outside of the or above the 15,000 volt range. And so that's the reason for today's presentation. And as we are wont to do, we like to start with a poll question. If you would please respond. The intent is to get a little bit of feedback on what your perspective is and reason for attending. And so if you will help us with some choices here, and on an average, how frequently do you encounter the need to deal with medium voltage greater than 15 kV? And obviously there's no obligation. We do appreciate some feedback from the folks using the tools or having to deal with in the real world. And our intent is to try to give you some tools and some options in doing just that. So we'll leave this open for another 5 seconds or so. Get everybody weighed in on it. Thank you for participating. Thank you for supporting EasyPower. And so here's how everybody weighed in on this question, which is about what you'd expect for the audience with this topic. And then the second question is, where is your main concern in terms of dealing with that range of voltage and arc flash at that range? So again, this is part of the area of confusion, and I think there's enough, I don't want to say misalignment, but lack of alignment between the different resources that that we want to talk about this, and getting your feedback, frankly, would be useful as well. So let's leave this question open for another 5 seconds. Looks like we're getting a quorum here. And let's see how everybody weighed in on this one. So, and these results actually are probably the basis of the confusion that we're dealing with. So let's kind of start there and get with it. So today's agenda is essentially talking about the changes in the 1584 that was released in early December of 2018, and the fact that there are no recommendations above 15K. We're going to revert to or depend on some other guidance that we have that's been around for several years in both the National Electrical Safety Code and in NFPA 70E. Then I'm going to walk through three examples using the EasyPower implementation of these standards, and hopefully offer some assistance as far as you're dealing with the problem. Now, before I get too far away from the topic, in the handout section of the control box for the webinar, I've put 2 documents. One is a practical solution guide to arc flash calculations, and the other is EasyPower apps note on line to ground arc flash, both of which cover this information in some detail. And so if you are not able to download that information, by all means you can contact me via email or contact tech support. All right, so NFPA 70E in the current version and the previous version of 1584 actually suggested that the Lee equations could be used in that they had the ability to calculate instant energy for open air three-phase arcs above 600 volts. But it was acknowledged that as you get to greater and greater voltage levels, that the results become more conservative, which means that the instant energy calculations are relatively high. And then when we get to the latest update on 1584, we find that it specifically has the scope that's limited to 15,000 volts. And outside of this scope, there's no recommendation, including nothing alluding to what to do about the Lee equations. And so we're kind of left out there with some amount of confusion over what to do about it. So that's why most of this time I'm going to be referring to a reference in NFPA 70E, which was released in 2009, that reflected tables that were also published in the ANSI C2 Table 410 and are still there today. And these tables, and in the D8 section of NFPA 70E 2009, were titled "The Estimated Instant Energy Exposure for Live Line Work on Overhead Open Air Systems." The significance to this title is that we're talking about a single line to ground model, and consequently that's the reason that a three-phase model, which is the purpose of the 1584 work, is primarily for three-phase arcs, balanced arcs. So what we're talking about here is a single line to ground and an open air. Now these tables, as published in NFPA 70E 2009, this is a reprint of table D8 number 1, specifically had these notes. And what it describes is these calculations are based on open air phase to ground arcs, and they have specific dimensions for the working distance. In this case, and for this particular table, was 15 inches, and the air gap is provided specifically for these range of voltages. So for 1 to 15K, the air gap is 2 inches for these calculations. For 15 to 25K, it's 4 inches. For 25K to 36K, 6. And for 36, the reason I'm going through this is that I'm going to show, as we go in and look at the different examples in EasyPower, that this is exactly and precisely what's been implemented in the EasyPower solution. Now, in these documents, it specifically refers to the fact that these calculations were derived on a commercially available computer program. Other methods are available, and effectively that's what we're talking about, is EasyPower equivalent method. At the time, it was fairly common knowledge that a piece of software called ArcPro was used to produce these results. And so what I'm in essence essentially showing or trying to demonstrate is this method that we have implemented is equivalent to or equal to or as acceptable as ArcPro. All right, then in table 8.2, the calculations were again based on open air phased ground faults. And the reason I have a couple of these data points highlighted is that these are the examples I'm going to walk through. So what this is telling us, in fact, let me go back to the other one. We're actually talking about a heat flux rate, which is a calories per centimeter squared per second. And so this allows us to, if we have some way to measure the time of the arc, then this will give us the ability to produce the heat radiation and the instant energy. And the method I'm going to use, and the other reason for kind of walking through this, some of the techniques of kind of doing this demonstration and walking through the proof that I would call this this demonstration of the equivalency is that some techniques that are useful, I think, if you have that as part of your EasyPower bag, and you'll see what I'm talking about when I get into it. All right, so again, what I'm going to do is create a circuit that has these properties, limit the time for calculations to 1 second, and that should give us these numbers that are highlighted, and they'll be in calories per square centimeter, which again is more a proof of the equivalency. It's not a real calculation for any particular system. Again, I want to emphasize that these are single line to ground models, and consequently that the time calculation is going to be something that you have to derive based upon your particular application, either with a worst case limitation on the time or with some known time limit that's implied upon the system by protective devices. All right, so a little bit of background on where all this stuff came from. We're going to be using single line to ground voltage, and basically we derive that by taking the phase-to-phase voltage and divide it by the square root of 3. And then, as we saw in the D3, let me back up. As we see here in the D2 notes, the air gap is calculated by taking the phase to ground and dividing by 10, because the dielectric of air is 10 kilovolts per inch. So at the higher voltages, arcs, once they're established, can be relatively stable, and it's commonly known that the dielectric strength of the air is going to be 10 kilovolts per inch. And likewise, the working distance recommended by these tables is based upon the minimum approach distance that's can be retrieved from ANSI C2, and then subtracting 2 times the gap length. And where I'm going to go with this is that you can use these default values, or the working distance is going to be something that you have control over. So that's what I'm doing here with some of this arithmetic, is that we're working out an air gap in inches, and if you put all this together, I can take my phase-to-phase voltage and come up with the air gap. And for instance, if we pick out a phase-to-phase voltage of 765 kilovolts, my air gap will end up being 44 inches, or 1123 millimeters. Now my working distance will end up being a factor or a function of that. If we look up the minimum approach distance and subtract 2 air gaps for 765 kilovolts, the minimum approach distance is 191 inches, and if we subtract from that 2 times my air gap, then our working distance for 765 will be 102 inches. So with a little bit of preparation and arithmetic, I've picked out 4 data points: 69 kilovolts, 242 kilovolts, 765, and just because these are data points on the chart, the short circuit line to ground, I'm going to use this to set up my example using these air gaps, and you'll see that in our results. All right, so let me jump into EasyPower and show how this works. So I've got 2 examples already created. I'm going to create a third and a fourth one, and the technique goes like this. I'm going to place a utility icon on the screen, place a bus on the screen, touch the utility. Now for this particular example, I want to do a 25.1 kV example, so let's type in 25.1 for my voltage. And then for my available current, and we're going to call this one 25.1 kV for my label. And let's just pick out the 5 available short circuit current. Now I don't care so much about the 3 phase to ground, so I'm just going to use the same value. What we're really basing the calculations on is the single line to ground. So we're going to use a basic 6 X over R. All right, so that's detailing my utility. Now the next step is I want to define this particular bus as open air. So above all else, I'm going to define it as open air. Now I have the ability to do some changing here from the standards, and we'll come back to that later. But from now, I just want to define this as open air. Now I go to short circuit focus. So I've got a specific amount of current. I've got a specific designation of open air on this bus and voltage. Now I go to short circuit focus. We're going to look at a single line to ground fault. I'm on the second row here at the top. Rather than normally picking out three-phase balance fault, I'm going to pick out a single line to ground, and we're going to fault the bus. Now, what I'm looking at, and I want to look at my arrange for arc flash. What I want to look at are these elements that went into the calculations, and they are a function of my short circuit options, my arc flash hazard tab. To set this up, I want to go to advanced. Now normally my advanced settings by default are going to be apply Ralph-Lee method. If I do that, you can see that my instant energy under 2002 won't yield any results because three phases is what Ralph-Lee is applied to. So at the very start, I need to uncheck the Ralph-Lee method and then select the open air method. And this is where I have a choice of picking out greater than 1 kilovolt or greater than 15. So everything we're doing here is greater than 15. And I'm going to stay with, now this is NFPA 70E is referring to those D8 2009 references that we talked about earlier. So as I apply those, I get an instant energy of 11.7 calories. Now the reason this is what it is I've limited my calculation time to 1 second. So again, I'm taking that chart, which showed me the heat flux rate, and I'm limiting calculation time to 1 second. And so what I expect to see is 11.6 calories per square centimeter is the instant energy calculated, and that's literally what I have, or virtually what I have. All right, so it's as simple as that. So I'm going to try this one more time. I'm going to go ahead and go back to database edit. We're going to deactivate this particular, I've got two other examples drawn here. I'm going to do this one more time. This time we're going to pick out 765, which I think I calculated for us. So let's go ahead and set up my utility, set up my bus. Set this up at 765 kilovolts. Let's go ahead and relabel it, retitle it, and then set my, let's go ahead and pick out 50,000 amps as my upper limit on line to ground. So I'm going to leave 50K in here, 6, 50K, and stay with 6. Now I go into short circuit focus. Again, I want single line to ground. I want my short circuit options to be advanced. Oh, actually I messed up. I want to go back to my database edit and define my bus as open air. This is probably the most critical part of the whole exercise. So once I've done that, now it allows me to invoke those short circuit options that are available under advanced, single line to ground, NFPA options, apply everything, fault the bus, look at my calculations. Now again, so this, I came up with the electrode gap. Let's go back and see what my calculations were. So this is why I did the my prep work on the math. Just to show that we've got this built into the tool. All right, so my working distance is 102 inches. So if I come over here, my working distance is 102 inches. My electrode gap is 1123 millimeters, And I got 1122 here. And then finally, we go to my, the D3 table, and I expect to see 25.3 calories, and I'm seeing 25.5 calories. Okay, so that's literally how you set it up. So now I'm going to go back to database edit and walk through a couple more examples just as data points. So I'm going to deactivate this. Now again, the technique that I'm referring to is the ability to put on multiple devices and deactivate multiple circuits and deactivate it, and then simulate a single bus exposure to a known amount of current. And so again, we've defined this bus as open air. Once we've done that, it makes it available to utilize the short circuit options under advanced. And we've selected apply open air D 2009, and we're staying with the working distance defined in the NFPA reference. We're going to fault the buses, look at my instant energy, and sure enough, I'm showing 41 calories. If we go back to my, and that's what we have here on the 252, I think it is, yeah, 242 voltage range. Okay, I'm going to do one more, and then offer a little bit more expanded application. So I'm going to deactivate this. And again, here we're going to do, in this one, 69 kilovolts, 20 amps, same process. Once I've defined my short circuit current to ground, define this particular bus as open air. Now, just as a departure from this, and this is to emphasize the fact that this is a tool, it's not one size fits all. When I select the NFP options and the advanced short circuit options, we are using that table lookup that we showed for arc gap and working distance. If I have the ability to control my working distance, EasyPower allows me to override the working distance default to whatever value I can make it. If I can make that distance farther out, then I would do so, which would lower the instant energy even more. So we'll show that in a second. When I go to short circuit options, again, if you have questions on this, you're welcome to contact me or tech support. But now that I have this defined as an open air bus, I have the ability to apply the NFPA open air equations. And here's where I supply I designate either the arc flash options or the numbers coming off the NFPA 70E chart. Once I apply this, I can do my short circuit arc fault, single line to ground, and arrange for arc flash. And now again, for my 69 volt range, I should see 12.5 calories. Right here is 12.4, and the working distance is 31 inches with an electrode gap of 101 inches. Okay, just before I jump into stuff a little bit more exotic, let me see if we've got any questions. All right, it looks like everybody's hanging in there with me. Now, the reason for putting it that way is that, now again, what I've been doing here is a technique of using a fixed 1 second calculation time, and all I'm doing that is verifying that the calculation method matches what's been recommended by the NESC or NFPA documents. What I want to jump to next is more of a real application, which is a one-line diagram that we've drawn up with equally clever techniques of controlling my current and voltages. But I have here several different levels of medium voltage, and this would be more indicative or related to, say, transmission line where we have several layers of different current and different time delays. But in this particular one line, I have both a 345 kilovolt bus that has a 1 second limit on it. And if I do that, if I go and look at the characterization of that bus, what I'd expect to see is an open air, and then I'm limiting the calculation time to 1 second on that one bus alone. And that's, if I go to short circuit focus, single line to ground, I'm going to pick out this one bus, fault it, and arrange for arc flash. What I see is an 8.4 calorie per square centimeter incident energy with electrode gap of 505 millimeters and a working distance of 70.2 inches, all of which is per those lookup tables that we described. And this is, again, based on a 1 second limit. Now, on the other hand, if I have a relay that's set up to trip and then operate a 3-cycle high voltage breaker, my calculations would look something like this. So if I fault this bus, we can see that the trip time on the relay is just over 1/4 of a second. The opening time on the breaker is 50 milliseconds. So now we have a maximum arcing time of 316 milliseconds, and we get an instant energy for the single line to ground on 345 kilovolts of 1.3 calories per square centimeter. Likewise, if we went to 121 kV, just to show that this at 1 second matches the rate on the NFPA 70E tables, we see with 177 millimeter air gap and a working distance of 26 inches for 121 kilovolts, we have an instant energy exposure of 24 calories for a 1 second exposure. If we control that with a relay, and let's say this relay is operating now with exposure to 6.3, we've put in the impedance that now brings that current down to 6.3 kiloamps. We can see that with a bolted fault current of 6.3 kiloamps, the trip time on the relay is going to be 437 milliseconds. Again, an opening time on the breaker of 50. That gives us an instant energy of 2.9 calories per square centimeter, along with the appropriate limited boundary and restricted boundary for electroshock. Okay, so this, be happy to send out this one-line diagram if you want to play with it to kind of satisfy yourself how this technique works. And I'm going to check to see if there's any other questions. It looks like we got one here. Let's see what we got. So the electrode gap on 69 shows 100 millimeter, table shows 101 inches. I guess I need to double check on that, which one we're talking about. So there's two different, 69 kV should not have that discrepancy. Okay. We had a correction on the question. I think I missed the reason why we want to only consider line to ground faults. Okay, and that's a good question. Let me kind of go back and illustrate what's going on. If you think in terms of high voltage applications, there's a separation between the phase conductors that would be very difficult to establish a three-phase fault. So that's why we work primarily off of a single phase to ground, because that's where typically an operator would be susceptible to an arcing flash. So that's the starting point. You'll notice once you get into the tools that there's the ability to elevate that calculation and carry that that instant energy into a two-line to ground fault as well as a phase-to-phase fault. And these are estimates because they're basically multiplication factors based upon the single line to ground fault model. So Saeed, I'm not sure you're saying, I'm not sure if I've got the question right, so you may need to contact me directly. Does EasyPower, okay, so Brendan's asking, the ARC Pro calculation that populate Table 3 have no sensitivity to source voltage if all other inputs are fixed. Changing source voltage doesn't affect instant energy. Can you comment on this? The answer is no, I can't comment on ARC Pro at all. What I can comment on is that chart in NESC, and it's all dependent upon voltage, because as you change voltage, you're changing the impedance that the arc presents to the current. So be more than happy to cover this offline, but that's, kind of talking about ArcPro is something I'm not really not the good resource for. Yeah, so anybody that wants that exercise, be happy to send it to you in a one-line folder diagram. And thank everyone for attending today. Basically, all we have to do is set up the bus dialog, make sure we have set it designated as open air, and then our arc short circuit options, go to the advanced open air selection, choose what voltage we have, and then make sure we're applying a single line to ground fault. And all this is documented in the handouts, which I would encourage you to download. If you have any trouble with those, let me know. Appreciate you all attending. Check in with the website. We've got regional training sites now announced for the rest of the year. And we have ongoing arc flash workshops walking around the country. Have a good day, everyone.